Hello all and welcome back. So in this video, let us continue our discussion on hash maps. And now let's see how are we going to handle the case of collision. So let's get started. Now in the last video, we saw that how internally we were creating a bucket array. So we were making a bucket array internally to implement our hash map. Let's say this is our bucket array. Now if you're giving me any particular value to store, let's say if you're giving me key 1, right? Then I used to take it via a hash function which used to give me a hash value and then compress, after which I used to save it in my bucket array. Now, the problem which arose after that was, let's say if we have a particular list which is having the size as 5. Okay, so it is having 5 size, and we have taken our overall hash function which gives us an integer value, and these are the values which I am getting. So let's say I get 50, 43, 47, 60 and 80. Okay, what used to happen was that if I will be now taking their modulo with respect to 5, okay, so modulus operator we used to apply to get or to compress our values so that they can fit into my bucket array. When I will be applying or getting their modulo, it will be 0, 3, 2, 0 and 0. So it is percentage 5. Now I can store 50 here. Similarly, I can store 43 here, 47 here. But the problem arises when I have to now store 60, right? So in this particular case, collision used to happen because I am saying that, hey, I want to store my value here, but 50 is already present. So this was the case in which we have to make sure or see how we can handle this collision, because collision is something which you cannot avoid. Collision can happen in two ways or two cases. First one is when we are having the same hash value. When we are compressing the same, we are getting the index which is similar, right? Just as in this case. Second is when we are trying to store more values than the size of an array. Okay, great. So let us discuss some techniques to handle the collision, everyone. So the first one is known as something open addressing. Okay, so open addressing. It is also called as closed hashing. Closed hashing. Now, what happened in this particular type of handling is that we say that you cannot come here. So let us see the example. 260, we are going to say that, hey, 60 is already present here and you cannot be stored here. So please go to the next position. If the place is empty, we are going to save. Else we are going to find an alternative. Okay, so let us write that down and let me copy this example as well. Great. So let us have this example here. And what effectively I'm saying is, in closed hashing, if default or rather initial place is empty, save it. Else find an alternative. So in this case, because for 50 we had the space, so we made sure that we are storing it here only, right? So we saved 50 first, but for 60 we will have to find an alternative. Okay, now the way alternative is found is that we have to find an alternate position, right? So we will be in a way recalculating our hash value, right? So let's see the formula for that, everyone. Also, one more thing, number of elements in this kind of hashing should be less than or equal to array or list size. Great. So let us see this, everyone. The formula is something like this. So g of I is equals to h of I, the initial hash function, whatever you are getting, plus k I dash. I dash is the number of try, percentage size. Okay, so it's pretty easy to implement, might be just seeing a little complex. Now say we have for 60, okay, for 60 initially we find out the value to be 0. Okay, we will be changing this value now, we will be finding some other value and then take the modulus again with size. This k of I dash, okay, this is actually a function, this is actually a function which we apply. Now there are different techniques, okay, so there can be different f of I. We can even make any of our own as well. So let me first write down few of the known ones. First is called linear probing. Linear probing. So what happen in linear probing is that I say that my k of I dash is going to be equal to I. Okay. So for the zeroth try, let me write this as well. I dash is equal to tries. Okay. For zeroth try, my final g of I is the final index, right? It's going to be exactly the same. It's going to be h of I plus 0 percentage size. So it is going to be h of I by size, which again is totally the same thing. I will be trying to store it at the initial value. If it fails, then what I will be doing is, it's easy to understand with respect to the visualization. So if 60 we are not able to save here, we will go one step forward and try to save it here. If it is also not available, we will go one step more forward. Again, if it is also not available, one step more forward. So this is what linear probing is. We are moving ahead by one size. So in this particular example, because it is not available, we will go and save 60 here. Okay. Similarly for 80, we will see that 50, then 60 will be present here, 47, 43, and finally we are going to save it here. The 80 will come here. Okay. Next time when you ask me to find the particular value, what I will do, I will go calculate the hash function for this particular 60. We'll go to 50. I will see that okay, it is not present, and I know that I have done linear programming. I will keep on moving because it is for sure that it would have been saved somewhere after 50, not before 50, right? So, for example, if something would have been after 47, 47 or some other number would have the same, then we will be going after it. One thing more, you can of course come back as well. So, for example, if this number, okay, so let me for a second change this example. Let's say we are saving 59 here. Okay, so let me change this to showcase one thing. We are saving 59 here and 69 here. Okay, the new overall hash function value for the index will be 4 and 4. First 59 will get and stored here. For 69, I will try to find percentage 5, which is coming out to be 4. Again, we know that at 4 value, 59 is already saved. Then what we are going to do, we are going to increase this by plus 1. So in the first try, so we say that the 0th try is where the hash function is the one which was given initially. In the next try, what we are going to do, we are going to add 1 to this. So 4 plus 1 percentage size, which is 5. And I will get 5 percentage 5, which is 0. Which means that I'm going to go and store my 69 here. Okay, everyone. So I hope this example is also clear that how it can be stored around your array. Okay, once the value increases beyond which it was, so it circles back to your array, right? Great. So this is what linear programming is. At each try, okay, so let me write that down as well. For each increasing try, we increase hash function linearly. Great. So that's the very first approach, everyone. Now let's talk about the second approach. Second approach is something which is known as quadratic probing. Again, the idea is that it should not happen if some place is a lot hotspot in our array. Okay, so let's say we are getting a lot of 40, 50, 60 based on a hash function. Okay, so in that we say that, hey, instead of going linearly, I am just going to go this time quadratically. Okay, so first I will just check the next position. So let's say if I take the example again, in this, or let me draw a new array overall, a little bit big one. So let's say this is my array or list. Let's say this particular is a very hot spot. Okay, so it is something which is a hot spot, like lots of elements are trying to come here. Now, if I try to just apply linear probing, then what will happen is I will make some overall places where lots of elements will get concentrated, right? Because many elements will try to come at this hotspot, and I will just save them after increasing them one by one. So the idea is again that we want to spread them out, right? So for that we use quadratic probing. First we increase by 1, then we increase by 4, then we increase by 9, then by 16, and like this in a squared manner. So the formula just become for the first try, it will be 1. For second try it will be 4. For third try it will be 9. Okay. And I know, I hope till now you would have and one thing clear, that we can have number of these uh, open addressing techniques, right? So we can tomorrow have, let's say, cubic probing, or even let's say we can have some square root or something. So we just have to make sure that we are trying to find a place for my array, right? We can maybe have a simple probing mechanism where we store to the last element, like the back of it. Okay. So that's the basic idea. There is one more which is used a lot. So let me share that as well. That is known as double hashing. Okay. So double hashing. What happen in double hashing is I will be applying another overall hash function. So my f of I is equals to I into h dash, okay, of I. So what happens here, everyone? The formula which we had initially was g of I, the final hash or the index value is something like this: g of I plus f of I and percentage size. This time my f of I is another hash function altogether. So we will apply another hash function and then get the index after taking the modulus. Now this hash function can again be anything, so that should not be a problem, right? We are just trying to find out the values. Okay, we are just trying to reduce the probability that lots of element, okay, they will be around each other. They will be basically, if they are coming to a particular hotspot or at a particular index, then I'm able to spread them out. I'm able to store them, make space for them. Okay. So that's the overall idea, everyone. Now let us see the next technique for handling the collision. It is known as closed addressing. So let me just write it down. The next technique is known as closed addressing. So let me make an array again and say we have some elements 50, 42, 49, 60 and 70. Right. And we have 5 spaces here. Now what happen in closed addressing is that we say they are going to be stored at a same position only. Like I will not be finding another position. Okay. So when I take the modulo by 5, the final index which I will be getting, and I'm assuming that the hash function is just the identity function giving me the same. So it will be 0, 2, 4, 0 and 0. And we know that this buckets array will be something like this. Here what we say is that yes, okay, you can store 0 here, 2 will go here, this will go here. When it comes to 60, I'm saying that it will get saved into the same position only. We will not be finding a new position. Okay, so effectively we will be storing 60 to the same position. Now how can I make sure that that happens? The way we handle that is we make, so let me write that down. We have each position of bucket array as head of linked list. So now it's not just a array or a list which is having space for an element. No, it is now containing head of linked list, right? So because of that, what happens now, if you will ask me that, hey, I want to store 60 at 50 place only. Okay, so let me just draw it as well, everyone. Let's say you are saying that, hey, I want to store 60 here only. This time it is actually a linked list. So it will not be stored like this. The way items are going to get stored is something like this. We will have a linked list here. Okay, so it will be 50. Then we will store 60. And then going forward, we can store 70 here as well. And each and every one of them are linked list. It's not that once we get the collision, then we convert it into a linked list. No, it is also a linked list. All of them are head of my linked list. It is also a linked list, a linked list, a linked list. Okay. So that is how we do closed addressing. It is also known as chaining because we are adding elements in chain, right, everyone? So just to repeat, what happens in closed addressing or chaining is that I say my element is going to get saved at the same position where I found out the overall index. Okay, after all the hashing and compressing everything. Now, to do that, we of course want to make sure that somehow we can store more than one elements into my buckets array at each and every index. So what we do is we create each and every index as head of my linked list, right? In a linked list, again, we know that how we can store more than one elements, and as and when the collision happens, we will be extending our linked list to store the element. Let's say for 50, we extended it to 60. Then when 70 comes, we will add 70 as well. So each and every index is a linked list head. Okay. So through this overall way, we are able to make sure that we are storing multiple items at a single position or an index. And we don't have to do rehashing or any of the open addressing technique to find out the hash function again or the value of the index again. Now, many of you might have this doubt that what if everything comes out here only? So there are ways to handle it. And one more doubt all of you might be having is that what if this becomes a lot long, right? So our whole aim when we started with the concept of hash map was that we wanted an O of one approach, right? A constant approach. But what if this linked list become a lot high in size? Well, there are multiple ways to handle it, which we are going to see, just go and see forward. One thing which you can also think of is that we can also make it in a way that it is stored by making a BST. We know that in BST the operations are pretty fast, right? So initially I talked that how linked list, BST, and this hash maps are used. Here you can also assume that it is a BST instead, where we know instead of O of n, the complexity is going to be O of log n. Okay, this is I think how in Java internally the hash maps are implemented. So that's also something which we can check out. We are going to learn about the linked list approach only. You now have an idea on BST, so of course you can do that as well. And we are also going to do the open addressing moving forward. Okay, so great everyone. I hope the whole discussion was clear. Please make sure that each and everything is properly understood. I have tried to explain using visualization as well. Going forward, when we code, I will again help you visualize from scratch each and everything so that you don't have any problem. Okay, so great everyone. Now let's meet in the next video where we will start with implementation of my hash maps.